Whether you were aware of it or not, I've been preparing you for this exciting moment in these calculus live lessons. All of the calculus theory that we've covered so far was building to this point where we could learn by hand how to calculate partial derivatives of cost with respect to model parameters. We'll then be able to use that information in code in order to confirm that the kinds of partial derivatives that we obtain using automated differentiation like PyTorch, that those values are the same as the values we could calculate by calculating derivatives by hand. In our single point regression notebook a moment ago, I showed you this quadratic cost formula, or this squared error formula for calculating cost. So we take our estimated y value that our model provides us, we subtract from that the true y value that we're trying to estimate, and then we square that difference, and that's quadratic cost. So if we'd like to calculate the partial derivative of cost with respect to one of our model parameters, which is determined by a function that produces y hat, we will first need to compute partial derivatives of c with respect to y hat. Conveniently for us, we can rely upon the chain rule here already. So we can consider this to be nested functions where we have the outer function of c being equal to u squared, and then u is equal to y hat minus y. Let's calculate the partial derivative of this equation here first. So we're only interested in the partial derivative of c with respect to y hat because the model parameters that we're interested in adjusting, m and b, are determined by a function that produces y hat. So we only need to calculate the partial derivative del u del y hat. And when we do that, we treat y as a constant, so it comes out to 0. Y hat, using the power rule, we know that this is y hat to the power of 1. When we use the power rule of differentiation, that y hat to the power of 1, the 1 moves in front, and y hat becomes y hat to the power of 0. Well, anything to the power of 0 becomes 1, and so we're left with 1 minus 0, and that's, of course, just 1. Okay, so that deals with the partial derivatives for one of our nested equations. Now what about the outer equation, c equals u squared? Well, here we can actually take the full derivative, which is the same as the partial derivative del c del u, and very simple with the power rule. 2 comes in front of the u, becomes 2u, and now we can substitute y hat minus y back in for u, leaving us with 2 times y hat minus y. Armed with the partial derivatives for both of our nested functions, del c del u and del u del y hat, we can use the chain rule to chain them together and calculate del c del y hat. So we chain together del c del u and del u del y hat, and because we're multiplying them, the del u's will cancel out. So del c del u is equal to this expression here, so we plop it here first, and then del u del y hat is simply equal to 1, so we can put that here, and of course multiplying 1 times the rest of this expression leaves us just with 2 times y hat minus y. Nice, so we now have del c del y hat, but we're also going to need to calculate some partial derivatives with respect to y hat in order to be able to chain c all the way back to our model parameters m and b. So let's go do that next. Remember our equation for a line. We've got y hat, our predicted y value, is a function of m times x plus b. Now here we have our model parameters, and we'd like to find the partial derivative of cost with respect to these two parameters. So given that we already have calculated del c del y hat, we can now go ahead and calculate y hat with respect to these model parameters m and b, and then later we can chain those to del c del y hat. We'll do that on the next slide coming up. So first, let's just focus on getting del y hat del m and del y hat del b. Pretty simple partial derivatives here. Let's start with del y hat del b. So for this partial derivative, we treat m as a constant, and a constant alone in its own term becomes 0 when we take its derivative. So we can just ignore that term, and b to the power of 1 becomes 1 times b to the power of 0, and anything to the power of 0 is 1. So 0 plus 1 gives us 1. So del y hat del b is just 1. For del y hat del m, here we're treating the variable b as a constant, and so in that case it zeroes out. And for our other term mx, use the power rule and the constant product rule to leave us with m to the power of 1, bring that 1 in front, becomes m to the power of 0, so this is just a 1. Constant product rule, we leave x hanging around, and so all we're left with in the end is a del y hat del m equal to x. Nice, we are almost there. We have all of the information we need now to chain cost all the way back through to our model parameters m and b. Let's have a look at it all together. So from 2 slides ago, we have del c del y hat. We know that that's equal to 2 times y hat minus y. So let's bring that here. And we know from the preceding slide that del y hat m is equal to x, and del y hat del b is equal to 1. So we can now rely on the chain rule to calculate del c del m and del c del b. Let's start with del c del m. We can chain together this expression del c del y hat with this expression del y hat del m. The del y hats cancel out and will leave us with del c del m. So substituting in for del c del y hat, we know that that's 2y hat minus y. And for del y hat del m, we know that that is equal to x, so we can bring it here. Simplifying the way that this looks a little bit by moving x inside the brackets, this comes out to 2x times y hat minus y. Nice, so this expression here allows us to calculate the slope of c with respect to our model parameter m. And finally, to get del c del b, we use the same kind of approach as we did for del c del m, except now we're using our del y hat del b expression, and otherwise this is the same. We have del c del y hat, so that's the same as from del c del m. It's this expression here. The only thing that's different is using del y hat b instead of del y hat m, and del y hat b is just equal to 1. So multiplying 1 through the rest of this expression leaves us just with 2 times y hat minus y. Nice, so now in addition to del c del m, we have del c del b, which is the quadratic cost with respect to our model parameter b. Awesome, we've got our quadratic cost with respect to all of our model parameters, which in our simple straight line regression is just 2 model parameters. Having used all of our partial derivative theory to calculate the partial derivative of cost with respect to our model parameters, we can now return to our single point regression notebook and confirm that the values we get by calculating these derivatives by hand are the same as the values we get by relying on an automated differentiation tool like PyTorch. So from the work that we just did in the slides, we know that del c del m is equal to this expression here, del c del b is equal to this expression here. So tackling del c del m first, I have Python code here that is the same as our expression, so it's 2 times x times y hat minus y. We have to use this item method here to extract the specific value that's stored in y hat, but there's nothing magical about that. So you can just consider this here to be y hat, the y hat variable, our single estimate 6.4 of what y should be. And we subtract from that the true y value, which is equal to negative 1.37. And then we multiply it by 2 times x, and that gives us 108. So our partial derivative, del C del m, our slope of quadratic cost with respect to our model parameter m, is equal to about 109. And it's the exact same value as we got when we relied on autodiff. Similarly, for del C del b, it's 2 times y hat minus y, so 2 times y hat minus y is equal to 15.5, which is the exact same value as we got calculating this partial derivative with autodiff in PyTorch. Sweet. Now that we have our partial derivatives of cost with respect to all of our model parameters, we can put them together into a single tensor called the gradient.